Okay, I'm going to talk about section 2.2, and we're going to talk about limit of a function and limit laws in this section. So make sure you have your lecture notes open from section 2.2 so that you can follow along, and you can find those lecture notes in Ivy Learn. All right, so the first thing we're going to talk about is limits of function values. So you can see in the notes it says when we're studying functions, we're often going to be interested in a function's behavior near a point, but not necessarily at that point. Sometimes we'll be interested in a point exactly, but sometimes near a point. So I have three different functions here, a, b, and c. Let's take a look at the function c first of all. So here we have h of x is equal to x plus 1. So let's see what happens when we graph this function. So we know when x is 0, if we plug 0 in for x, the value of the function is going to be 1. So we know that we have a point right here at 0, 1. And then if we were going to plug in negative 1 into that function, we know that our y value is going to be 0, so negative 1, 0 is a point. And if we plug in x is equal to 1, our y value is going to be 1 plus 1, or it's going to be equal to 2. All right, so we have a point at 1, 2. And this is a graph of a line, so we can connect all of those points with a straight line. That'll look like this. All right, then we can talk about the concept of a limit. So we're going to say that the limit as x approaches, oops, that's a little messy here. Okay, let me just rewrite that. All right, so the limit as x approaches 1, and then I'm going to write this function of this function, and we want to see what that's equal to. So we're looking at what's happening to this function, to this line, as x is getting close to 1. So here's our x value of 1, and we're looking at values of x that are getting close to that value. And what's happening to this function? This function is x plus 1. So we can see what's happening exactly at 1. It's going to be 2. And then we're looking at what's happening to those y values, as we're getting close to those values of 1. And you can see that when we approach 1 from the left-hand side, if we get closer to 1 from the left-hand side, the value of our function is around here. And when we approach 1 from the right-hand side, the value of the function is around here. But all of those values are getting close to 2. And if we were to plug 1 into that function, we would have x is equal to 1 plus 1. And so that's 2. So the limit of that function is going to be 2 as we get close to 1. So sometimes we can plug that number directly into that function, and we can see the exact y value by plugging that number into the function. But if we look at example A, we're going to see that sometimes we can't plug that number directly into our function, because now we're asking the question, what's happening to this function here, f of x is equal to x squared minus 1 over x divided by x minus 1, when x is equal to 1. If we plug a 1 into that function, the denominator is 0, and so we can't evaluate that directly. So let's graph this though and see what's happening. So if we were going to plug in a negative 1 into this function, in the numerator we're going to have negative 1 squared, which is 1 minus 1, and that's going to be 0. And that's going to be divided by negative 2. So it's still going to be a 0. And then if we were going to plug in a 0, we have negative 1 divided by negative 1, which is 1. So the value of our function at 0 is 1. Okay, so just like before. But now when we plug in a 1, if we plug in a 1 into the function, that function is going to be undefined at 1, because we can't plug in a 1 in the denominator because we have a 0 and we can't divide by 0, so it's going to be undefined. When we end up graphing this function, it's going to be a line, the same line as what we had for example C here, except now we're going to have an open circle at 1. So it's going to be undefined at 1. There's no value of the function. But this is going to be a line, just like the same line as we had in example C, except we have an open circle at 1. And we can see that by factoring this function as well. X minus 1 factors as x minus 1 times x plus 1 divided by x minus 1. And if we cancel those x minus 1 factors, we're left with x plus 1, which is that same function that we had before. We just can't fill that circle in at 1, 2 because the original function is still undefined at 1. All right, so now let's look and see what's happening with this limit. The limit as x goes to 1, and now we're looking at this function. Let me see, I'm going to write it down a little lower. I'll write it down right here. So, oops. All right, so the limit as x approaches 1, and now we have a new function, x squared minus 1 over x minus 1. So what we want to do is we want to look at the graph of this function and see what's happening again when x is getting close to 1. So if we're getting close to 1, we can look at it from the left-hand side and from the right-hand side. The x values are getting close to here. What's happening to our y values up here on the graph? What are our y values getting close to? It doesn't matter that it's not defined exactly at 1. We're looking at what is it getting close to. When our x values are getting close to 1, what are our y values approaching? What are our y values approaching? So this one still is going to be getting close to 2. The y values, when we get, for example, if we're looking at 1.01 or if we're looking at 0.999, those values, those y values are still going to be close to 2. So we're still going to say that the limit of x squared minus 1 over x minus 1 is going to be equal to 2. And then let's look at b for this function, g of x. So this function starts off as a piecewise defined function. It still is the same function that we had before, x squared minus 1 over x minus 1, as long as x isn't equal to 1. So we can graph that because it's the exact same thing as what we had in part A. All right. So we have negative 1, 0. We have 0, 1. We have 1, 2 is still going to be an open circle. Just like before, we have the same line that we had before. We have that open circle there. And the difference now is that we have part of this piecewise defined function has a second part that now says that g of x is going to be equal to 1 when x is equal to 1. So when x is 1 now, we're saying that our function is defined and the y value is going to be 1 when x is 1. So this is saying y is equal to 1 when x is 1. So we have an actual value of that. And then we can find the limit of this function. So we can talk about the limit. So let's see. I'll write it down here. The limit when x gets close to 1 of this piecewise defined function. So this is x squared minus 1 over x minus 1. When x is not equal to 1, and it's equal to 1 when x is equal to 1. So that's what our function is. All right, so let me erase this one over here, get this out of the way. All right, so we want to talk about what this specific limit is now. And again, we're going to look at the graph that we have of this function for part B. And we want to see what's happening when x is getting close to 1. Let's put that 1 in there. Again, what's happening when x is getting close to 1? So the same thing is happening when x is getting close to 1. All of these y values are getting close to 2. The y values are close to 2. And it doesn't matter that at this specific point, the y value is 1. We're just talking about what's happening in general. As our x values are getting close to 1, our y values are going to be getting closer and closer and closer to 2. So again, it doesn't matter if that specific value at 1 now is being defined at 1. As we get close to 1, this function is still approaching 2. So we're going to say that the limit is going to be equal to 2 for that function. All right. So let me erase all of this stuff, and we'll talk about some more specific functions then. All right, So let's talk about the identity function. And we know that the identity function f of x is equal to x. And just to recall, f of x f of x is equal to x means y is equal to x. Same thing as saying y is equal to x. So when we graph the identity function, we're just saying that whatever the value of x is, y is that same value. So 0, 0 is going to be a point on the graph. 0, 0 is a point. 1, 1 is a point. 2, 2 is a point. -1, -1 is a point. And we can connect all of those points with a straight line. And the identity function looks like this. So if we're talking about a limit for this function, so looking at the one that I just drew, let's say we're looking at the limit as x approaches, let's say 1, for example. As x approaches 1 of f of x, which is our function. So as our function is getting, as our x values are approaching 1, we can see that the y values are getting close to 1 as well. So the limit as x approaches 1 of this identity function is going to be equal to 1. And we could do another one. We could say, what is the limit as x approaches 2 of this function? So our function is f of x. As we get close to 2, as our x values get close to 2, the y values are also getting close to 2. So that limit is going to be equal to 2. The limit as x approaches 3 of that function is going to be 3. So in general, for any value of c, the limit as x approaches c, and c can be anything, of our function is going to be equal to whatever c is. So if c is 4, the limit is going to be equal to 4. If c is -1, the limit is going to be equal to -1. So drawing another picture just in general here, that should be going through the origin. So let me see if I can do that a little better. Okay. So let's say this is c right here, and the limit is going to be equal to whatever the y value is, which is going to be the same thing as c. So this is for a function, specifically the identity function y is equal to x. All right, then we can talk about the constant function. And let's just recall what the constant function is. If f is a constant function, f of x is equal to k. It's a function with the constant value k. So k is a constant, it's a number. So f of x is the same thing as y. So we could say, for example, y is equal to 4. And we can draw this function. So this means that for any value of x, we know it doesn't matter what the value of x is, the y value is always going to be equal to 4. So it's going to be a horizontal line that goes through 4. So if we were going to look at the limit, and we can talk about any value of c. So for example, we can say the limit as x approaches some value c. Let's say c is equal to 2. It doesn't matter. And this is our function f of x. So as x approaches 2, let's say it's approaching 2 right here, what is our y value? You can see our y value is going to be 4. And we can do another one, the limit as x approaches -3, for example, of this function that we have drawn here. So if this is -3 and x is getting close to -3, what is our y value getting close to? It's getting close to 4. So in general, we can draw a general picture right here. Let's say that this is going to be our function. This is our value k, whatever it is here. It could be anything. And now this line is going to be y is equal to k. And we can pick any value c, and again, c can be any x value, but if we pick any value of c, the limit is going to still be equal to whatever k is. So the limit as x approaches c of k is always going to be equal to k, whatever that is. All right, then let's go to the next page on your notes, and it says that a function may not have a limit at a particular point. So some ways that limits can fail to exist are going to be shown below, and we're going to be finding the limit as x approaches 0. So let's look at a couple of these examples. So let's draw this first function right here. This is a piecewise defined function. And remember, it consists of two parts. So really we're looking at two separate functions here. We're first looking at y is equal to 0 whenever x is less than 0. So whenever x is a negative number, y is going to be 0. And y is equal to 1 whenever x is a positive number or 0. So it's kind of like graphing two separate functions onto one graph. So let's do the first one. Y is equal to 0 whenever x is less than 0. So it can't be 0, so we'll put an open circle there. And then negative numbers, we can just highlight on that x-axis like that. And then y is equal to 1. So our y values are always going to be 1 when x is greater than or equal to 0. So starting at 0 and getting positive, our y values are going to be equal to 1. So this graph is going to look like this. And let's talk about the limit now. So we're being asked to find the limit as x approaches 0. So we want to find the limit as x approaches 0 of this function. And here I have it called y, but I'm just going to write it as, call it function f of x. So let's look at what's happening as our x values are getting close to 0. So 0 is right here. And let's look and see what's happening maybe to the left of 0 and maybe to the right of 0. So to the left of 0, we're on this line right here, and our y values are all going to be 0. So the function is approaching 0 to the left of 0. And if we look to the right of 0, and our values to the right of 0 get closer and closer to 0, we're up here on this part of the graph, and our y values approach 1. So here our y values are 0, here our y values are 1, as we get closer and closer to x is equal to 0. So they're not the same, so this function does not have a limit. So we're going to say this limit as x approaches 0 of f of x does not exist, and we're going to abbreviate does not exist as DNE. So it does not exist as DNE. All right, let's look at another example for part B. And again, it's a piecewise defined function. Y is equal to 1 over x whenever x is not equal to 0. So we can draw that. So we know that when x is 1, y is 1. So 1 comma 1 is a point. When x is 2, y is 1/2. When x is 1/2, y is 2. And this is a reciprocal function, so we can draw this like this. There's asymptote at x is equal to 0 and y is equal to 0. And it's also defined down here in this quadrant. And it looks like this in this quadrant. So that's the first part of the piecewise defined function. And the second part says that y is equal to 0. So I could erase this part. And the second part says that y is equal to 0 whenever x is equal to 0. So the first one wasn't defined when x is 0, but now we're saying when x is 0, y is 0. So we have this additional point right here in this graph. All right, so let's do the same thing. Let's look and see what's happening to our y values as our x values get closer and closer to 0. So again, we're kind of looking at x values to the left of this point right here and to the right. So if I look at what's happening to the left of 0, my y values are down here. And they just keep getting more and more negative, bigger and bigger and bigger negatively down here. And then if I look and see what's happening to the right of 0, so these values of x right here, what's happening to the y values? The y values are here, and they're getting bigger and bigger positively in this direction. But they're definitely not approaching the same number. So they're definitely approaching different numbers. So again, we're going to say that the limit as x approaches 0 of this function f of x also does not exist. So that's a second way that limits cannot exist. And the third example for C here is y is equal to 0 whenever x is less than 0. So we'll put an open circle here and our y values are going to be 0 whenever x values are negative. And then y is going to be equal to the sign of 1 over x when x is a positive number. So sign is going to be fluctuating between -1 and 1, and our reciprocal sign of 1 over x is going to do the same thing. And it's going to be a really super tight graph in the beginning here where it just fluctuates back and forth between 1 and -1. And then it just starts to get a little wider, but it just continues to fluctuate between -1 and 1. So if we're talking about a limit as x approaches 0 of f of x again, we can see that to the left of 0, our y values are all going to be 0. And to the right of 0, all over here along this graph, all the values of y are going to constantly fluctuate between 1 and -1. So this is another way that a limit can fail to exist. So that one also does not exist. All right, then number 2 on your handout here is talking about limit laws. And when we have limits and we have more than one function, so in this case we have a function f and we have a function g. So we're talking about each of these, the limits of each of these functions approaching the same number c, and we'll call the limit of function f L, and we'll call the limit of function g m. So those are numbers. L and m are numbers. They're the limit as x approaches c for each one of those functions. And it's nice, the way that the limit laws work is the way that we would like them to work. So for example, we have the sum rule that says if we're taking the limit of the sum of two functions, if we're taking f of x plus g of x, it works nicely because we can just add those two limits together and we can get L plus m. The difference rule works the same way when we're taking a limit of two functions that we're subtracting. We're finding the difference, f of x minus g of x. The limits also can be subtracted. We can find the difference of those limits, L minus m. Constant multiplier, if we have a limit of a constant k times a function, we can take that constant, we can pull it out to the front, and really we're looking at c times a limit of f of x. But since we know that the limit of f of x is L, this ends up being k times L. So we can just multiply that limit by that constant. And product rule behaves the way that we would like it to behave. We can just multiply those limits. When we're taking a limit of a product, we can just take the product of the limits, so L times M. Quotient rule, same way. We can take the quotient of the limits. We can find, just say that the limit of f of x over g of x is L over m, as long as m isn't 0, because we can't divide by 0. And the power rule, if we have the limit of f of x to the nth power, is just that limit L to the nth power, and works the same way for roots as well. All right, so the limit of the nth root of f of x is the nth root of whatever that limit L is. Okay, let's look specifically at polynomials then. So we have a theorem 2, talks about limits of polynomials. So p of x is a polynomial. The way that we write polynomials, can have a constant in front of x, and that constant in front of it, a sub n minus 1, can be any number. And then we have the powers of x, and x to the n minus 1, and those powers have to be positive integers. All right, so let's look at the next page then. Oh, first of all, let me talk about what the rest of this limit says. So this limit says that when we have a polynomial, p of x, and we're taking the limit as x is getting close to a number c, all we have to do is evaluate p of c. So we just have to take c, whatever c is, and we're just going to plug it into the function wherever we see an x. So we're going to take that number c, and we're going to plug it in here wherever we see an x. And that's going to be the limit. So the limit of these polynomials are going to be easy to find because all you're doing is plugging that number in. So we can look at this first example as x approaches 2 of this polynomial negative x squared plus 5x minus 2. And we're plugging in 2 into this polynomial. And we have the opposite of 2 squared. So be careful when you're plugging that in. You're not plugging in a negative 2, plugging in a positive 2, and then you're making it negative after you square it. Plus 5 times 2 minus 2 is equal to 2 squared, 4, plus 10 minus 2, and that's 14. Or this one's, I forgot to put the negative in front here, so let's make this negative. So negative 4 plus 10 is 6 minus 2, and that's going to be equal to 4. So that's the limit of that polynomial as x gets close to 2. And then we have another theorem. So theorem 3, limits of rational functions. So now we have two polynomial functions. P is a polynomial function, and Q is a polynomial function. And we're looking at the limit of a rational function where the numerator is a polynomial P, the denominator is a polynomial Q, and we can do the same thing. We can plug C into our function P, and we can plug C into our function Q. So here's an example. Polynomial in the numerator, polynomial in the denominator, and we're just going to plug 2 in for y down here, plug 2 in for y up here. So this limit is going to be equal to 2 plus 2 divided by 2 squared plus 5 times 2 plus 6. And that's going to be equal to 4 in the numerator and 4 plus 10 plus 6 in the denominator, so that's going to be 4 over 20, which is equal to 1/5. All right. Part 3, eliminating common factors from 0 denominators. So theorem 3, the theorem that we just did, applies only if the denominator is not 0 at C. So theorem 3, everything would be really great if we could just plug a number into every function that we have. But it doesn't always work that way because sometimes the denominators end up being 0. So if the denominator is 0, we have to try to use algebra or try to factor. So when we say algebra, maybe we can simplify a polynomial, a numerator, denominator. Maybe we can add or subtract. Or we can try to factor. And canceling common factors in the numerator and denominator may allow us to find the limit by substitution. So what we're looking at is trying to find common factors if we have a problem in the denominator that maybe we can cancel. So if we look at part A here, if we were to plug in a -1, because that's what we always want to try. We always want to try to see if we can plug that into the numerator and denominator. But what happens when we plug in a -1 into the denominator? We get -1 squared minus a -1 minus 2. That's equal to 1 plus 1 minus 2, which is equal to 0. So that's a problem. We can't just plug that -1 in because we can't have a 0 in the denominator. So instead, we're going to try to use algebra or try to factor. So there's really no algebra to do. So we'll see if there's something that we can factor. So we're looking at the limit as t goes to -1. And then we're going to try to factor the numerator and the denominator. This one factors as t plus 1 times t plus 2. And the denominator factors as t minus 2 times t plus 1. And then you can see common factors in the numerator and the denominator. So t plus 1 is a common factor, so you can divide out or cancel those common factors. And we're left with the limit as t goes to -1 of t plus 2 over t minus 2. And now we're going to try the same thing that we tried in the beginning. We're going to try to plug in that -1 in the polynomial in the numerator and denominator and see if there's any problems. This time when we plug a -1 into the denominator, we have -1 minus 2, which isn't 0, so it's fine. We can do that. And then when we plug -1 in the numerator, we get -1 plus 2. And this is going to be equal to 1 divided by -3. And you can multiply the top and the bottom by a -1. So this is the same thing as -1/3. Let me write the negative in the front here. So -1/3. All right, then let's take a look at B. At this function here. And now we're looking at the limit as x approaches 1 of 1 over x minus 1 over x minus 1. And you can see easily on this one, if we were to try to plug a 1 into the denominator, this denominator is going to go to 0, and that's a problem. So we can't plug a 1 in. So instead, we want to try to use algebra, or we want to try to factor. So there's really nothing to factor here, but we can try to use a little algebra in order to maybe simplify that numerator. So we could try to, well, we could factor. I guess we could factor an x out of the numerator and denominator, or we could think about getting rid of that fraction by multiplying the top and the bottom by an x. So either way, you can think about it as factoring or simplifying that fraction in the numerator. So this is going to be the limit as x approaches 1 of, so let's factor an x out of the numerator. Or so instead of factoring an x out, let's clear the fraction, like I said. So let's multiply the top and the bottom by x in order to clear that fraction. And then multiply the bottom by x as well. So if you multiply the top by x to clear the fraction, you got to multiply the bottom by x. And this is the limit as x goes to 1. And then if you distribute that x in the top, the x's cancel for the first term, and you're left with just a 1. And then when you distribute the x to the 1, you get minus x in the numerator. And then the denominator, we can leave that as factored because we're going to look to see if there's any common factors for us to cancel. So we don't want to distribute in the denominator. So don't distribute. So the whole point is looking for a common factor to cancel. And if we distributed the denominator and we got x squared minus x, we wouldn't be able to see anything that would need to be, that we could possibly cancel. So we want to leave it factored. So the denominator is going to be x times x minus 1. Okay. Now we look at this and we see in the numerator, what we have in the numerator is very close to what we have in the denominator. 1 minus x is really close to x minus 1. So we're going to see if there's anything that we can do to make these things, the numerator and the denominator, the same. All right, so 1 minus x is the same thing as negative x plus 1. So we have this negative x plus 1. And again, that's really close to x minus 1. We just have the signs that are the opposite. So we could try to factor out a negative 1 in the numerator. When we do that, if we factor out a negative 1 in the numerator, the 1 becomes negative, and the minus x becomes plus x. And then you should distribute that negative 1 just to convince yourself that what we just wrote was exactly the same as the previous step. Negative 1 times negative 1 is 1. Negative 1 times x is minus x. So it's the same thing as what we just wrote. And I'm just going to copy x times x minus 1. And now we have a common factor that we can cancel because x minus 1 is the same thing as negative 1 plus x. These are exactly the same now, and we can cancel them. So now what we're left with is the limit as x approaches 1 of negative 1 divided by x. And now we can try to plug that 1 in again, And now when we do that, we don't have division by 0. We got rid of the problem. So now we have negative 1 divided by 1, which is equal to negative 1. So that's what our limit is for this problem. All right, so a couple things that you can always try to do would be try using some algebra, like we did for that first one, by simplifying that fraction, or that was for the second one, or try factoring like we did for the first time. But sometimes you can't create that common factor, or sometimes you can create a common factor by multiplying the numerator and the denominator by the conjugate radical expression. So if you're looking at this example here, there's nothing for us to factor, and there's really no algebra for us to do, like there's no fraction for us to try and simplify. But we have this radical here, and we're going to multiply by the conjugate radical expression. So the conjugate means that we're going to do the opposite. So if we're starting with something that's addition, we're going to write subtraction, and if we're starting with something that's addition, we're going to write, if we're starting with something that's subtraction, we're going to write addition. So the opposite. And we're going to look at the radical expression. So our radical expression is that square root of x squared plus 8, and then we have the minus 3 in the numerator. So the way that we're going to deal with this is to multiply the top and the bottom by the conjugate radical expression. So in this case, the conjugate radical expression is going to be the square root of x squared plus 8, and now it's going to be plus 3. Instead of minus 3, it's going to be plus 3. And we have to multiply the top and the bottom by the same thing. And the 3, oops, that's not what I meant to write there. All right, let's redo this here. Square root of x squared plus 8 minus 3. And this is the square root of x squared plus 8 minus 3. So we're multiplying the top and the bottom by the same thing. And the reason that we're doing that is if we try to plug in that negative 1 in the very beginning, we end up with a 0 in the denominator, which we can't have. So we have to do something about it. So we're trying to get a common factor that we can cancel in order to get rid of this problem that we have in the denominator. Okay. So we have to FOIL the top and the bottom. So we're multiplying these first terms. So when we FOIL, we're multiplying this x squared plus 8 times the square root of x squared plus 8 times the square root of x squared plus 8. So that ends up being x squared plus 8. So we can get rid of the radicals. And then we have our inside term, which is, oh wait, I mean, these need to be pluses here. I said that we're multiplying by the opposite, which has to be a plus sign. So both of these have to be plus 3, not minus 3. Okay. And the middle terms are going to cancel because we have minus 3 times the square root of x squared plus 8 plus 3 times the square root of x squared plus 8. So the inside terms and the outside terms are going to cancel. And then we're going to multiply the last terms, minus 3 times plus 3, and get minus 9 in the numerator after we FOIL. And then again, just like the last problem, we're not going to FOIL that denominator because we're looking for common factors. And if we would FOIL it, it's just going to make it look a lot messier. And we're looking for a common factor to cancel anyway. So we're going to leave the denominator factored. So it's already factored like this, x plus 1 times square root of x squared plus 8 plus 3. So that's factored, so we're going to leave that alone. All right, so keep this factored. Factored. All right, let's simplify what we have. We have the limit as x approaches -1. And the numerator now, x squared plus 8 minus 1 is just x squared minus 1. And just copy that denominator. I know it looks like a mess, but we're just going to copy it. So I'm not doing anything with the denominator. X squared plus 8 plus 3. All right, now we can see we're still looking for the common factor that we can cancel. So we can look at the numerator x squared minus 1 and we can factor that. That's going to factor as x plus 1, it's a difference of 2 squares, times x minus 1. And then again copy that denominator. And now we have that common factor that we can cancel. So that is our whole goal here, is to get that common factor. That's the thing that was causing us trouble in the beginning. This was our problem, the x plus 1. So now we're getting rid of that problem. So when we plug in that -1, we're not going to get a 0 anymore. So now we're looking at the limit as x goes to -1. What we have left is x minus 1 in the numerator and the square root of x squared plus 8 plus 3 in the denominator. Make sure you don't put the 3 under the radical. Now we can plug in a -1 in the numerator and the denominator without getting a 0 in the denominator. So in the denominator, when we plug in a -1, we have the square root of 1 plus 8. So we have the square root of 9 plus 3. And in the numerator, when we plug in a -1, we're going to have -2. So this is going to be equal to -2 in the numerator. And in the denominator, we're going to have a 6. And so this limit is going to be equal to -1/3. All right, then I have two problems here. I have problem A and B, and I want you to try these two problems. So for the first one, you're going to try and get rid of that radical in the denominator by multiplying by the conjugate radical expression, which would be the square root of x squared plus 5 plus 3. Because when you try to plug in this -2 into this denominator the way that it is, you end up with a problem. You have the square root of 4 plus 5, which is 9, plus -3, and square root of 4 plus 9 is 3 minus 3. This thing goes to 0, so that's a problem. So we want to get rid of that problem. And then in the second one, you're going to try to eliminate the fractions here by doing a little bit of algebra. So you can either add those two expressions in the numerator and then do the division with the numerator and the denominator, or you can try to clear those fractions by multiplying the numerator and denominator by the least common multiple of the denominators. So go ahead and try that. All right, so I did the first step for this one. I showed that I'm multiplying the top and the bottom by the conjugate radical expression, which is a square root of x squared plus 5 plus 3 this time. And the plus 3 is going to allow those inside and outside terms to cancel in the denominator. So if we FOIL the denominator, the square root of x squared plus 5 times the square root of x squared plus 5, you should have gotten x squared plus 5. Inside and outside terms cancel, and then the last term is -3 minus 3 times plus 3 is going to be -9 in the denominator. This time, since we were multiplying by the conjugate of the denominator, now we have that numerator that we want to keep factored. We don't want to FOIL that numerator and make it more of a mess. So we're going to keep that numerator the same. We're going to keep it factored. Because now we're going to look for a common factor in the denominator this time. So we want to keep things factored if they already are, and if they're not factored, we want to try and factor them. The whole point is to factor them. All right, then this is the limit as x goes to -2. I'm going to keep the numerator the same. And the denominator now is x squared minus 4. And then we can see that this is going to behave just like that last problem that we did. Because the denominator, again, is going to be the difference of two squares that we can factor. And that denominator is going to factor as x plus 2 times x minus 2. So just like before, we can cancel the x plus 2 in the numerator with the x plus 2 in the denominator. And that gets rid of our problem because we're looking at what happens when x approaches -2. We want to be able to plug -2 in, and we can't plug it into x plus 2. So now we have the limit as x approaches -2 of square root of x squared plus 5 plus 3 divided by x minus 2. Now we can plug that -2 in. So let's do that. In the denominator, we get -2 minus 2, which isn't a problem. In the numerator, we get the square root of -2 squared is 4, plus 5 is going to be the square root of 9, plus 3, and that's going to be the square root of 3, the square root of 9, which is 3, plus 3, that's going to be 6, divided by -4, and then simplifying that, that's going to be -3 halves. So that's what our limit is going to be equal to. All right, then let's take a look at the next one. And I said there's two different ways that you could do this one. You could do the addition, like I said, get a common denominator in the numerator for each one of those terms, get a common denominator and add those fractions and then divide that complex fraction. Or you could try to clear the fractions by multiplying the top and the bottom by the least common denominator of each of those denominators. So that's the technique that I'm going to do for this one. So the limit as x approaches 0 of, and our least common denominator for each one of these fractions, if we look at each one of these fractions, the least common denominator is going to be x minus 1 times x plus 1. So if I want to clear those fractions, get rid of those fractions, that's what I'm going to multiply the top and the bottom of this whole fraction by. So I'm going to multiply that first term by x minus 1 times x plus 1. Well, actually, I'm going to just show that. I'm going to do this one extra step here. So I'm saying I'm going to multiply the top by x minus 1 times x plus 1. And so here's my original fraction. I'm going to multiply that by x minus 1 times x plus 1. And I'm going to multiply the denominator by x minus 1 times x plus 1 as well. Okay, and that's going to be multiplied by this x over here. So then I have to distribute this inside here and to here. So everything gets multiplied by that least common denominator. And when you do that, you still have a limit. X goes to 0. And when we multiply x minus 1 times x plus 1 times this first fraction, I'll write it out so that you can see it. So I'm just going to write it out before I actually do the multiplication. So this is times that first fraction. And then this is going to be minus. I wrote that up a little too high. Maybe I'll move that down a little bit, make it easier to read. Okay, let me rewrite that. All right, x minus 1 times x plus 1 times 1 over x minus 1 minus x minus 1 times x plus 1. So I'm distributing the x minus 1 times the x plus 1 to each one of those fractions in the numerator. And then that's divided by x minus 1 times x plus 1 times x. Okay. So I haven't done anything yet, just showed, well, I've just distributed that least common denominator inside to the two terms in that numerator. Now when we multiply this first one, the x minus 1s can cancel, and we're left with, I'll write that limit as x goes to 0. We're left with x plus 1 for the first one. And then for the second one, the x plus 1s cancel, and we're left with minus x minus 1. So we have to be careful to put that in parentheses. And then the denominator, we'll keep it factored. All right, still looking at common factors that we can cancel. So the numerator becomes x plus 1, and we have to distribute that minus inside the into the numerator. So the numerator is x plus 1 minus x plus 1, and the denominator is still factored. All right, then we have in the numerator x minus x is 0, and 1 plus 1 is 2. Or x minus x, x plus 1 plus x minus x. All right. Oh, okay, over here when I drew a line right here through this, I thought this was a minus sign, but this was a plus. So this whole time I've been writing it as a minus because I covered up that plus sign. So I need to fix this and make this a minus, a plus here. And this is a plus. This, let's see, should be a plus, right? And then this becomes a plus down here. And then this was a minus here. All right, so I just copied that problem down wrong. All right, I think that'll take care of this then. So x plus x is 2x in the numerator, and 1 minus 1 is 0. And then the denominator, just copying that. And the x's cancel from the numerator and denominator, and then we're left with just a 2 in the numerator and just that x minus 1 times x plus 1 in the denominator. So now when we plug in a 0 into this function, we get 2 divided by, and that's going to be a negative 1 times a positive 1. So that's 2 divided by negative 1, and this limit ends up being negative 2. And that will take care of section 2.2.